Thanks for having me here. I'm not going to deliberately try to be as provocative as Joe, so maybe you can just try to be nicer to me. But it is my opinion that it's impossible to talk about feedback, galactic scale winds, and quenching without discussing the circumgalactic medium, and that is the diffuse gas extending to the virial radius around galaxies. I'm not going to talk about quasars. I'm not going to talk about one galaxy. I'm going to talk about normal galaxies in the low redshift universe. So the CGM is where accreting flows meet outflowing gas, and therefore the structure and the composition of the circumgalactic medium is intimately related to both the history and the future of the galaxy. If it is a lack of cool gas flows that terminate star formation in galaxies, the CGM would presumably reflect this. If the interstellar material of quiescent galaxies is ejected into their surroundings, the CGM would presumably reflect this. And if there's some mechanism keeping galaxies dead, the CGM could reflect this. And so along these lines, I'm going to talk about absorption line studies of circumgalactic gas, and in particular, one survey that I've worked a lot on called cos halos, which I'll define in a little bit. But there are three observational realities that I think are relevant to discussions of quenching and quiescence at this conference, that any theory of quenching and quiescence must account for. And that is all L-star galaxies, including quiescent galaxies, show significant H1 absorption in other cool metal ions to 150 kiloparsecs. This cool gas is highly ionized and metal enriched, and there's enough of it to account for at least 50% of the baryon budget of an L-star halo. The red-blue dichotomy of the galaxy population is reflected by the strong presence of oxygen-6, that is warm gas, around star-forming galaxies, and its absence around non-star-forming galaxies. And so as I go through this talk, I'm going to address each of these points one by one and show you some data to back it up. But first, let me just tell you a little bit about cos halos and why it's different from previous absorption line surveys. Limited by the instruments and the frequency of quasars on the sky, previous studies tended to conduct surveys looking for quasars, taking an absorption line spectrum, finding an absorber, that is, an absorber being a series of absorption lines that match up to a particular redshift, then going and hunting for a galaxy at that redshift in a deep image of the quasar field with spectra. So cos halos instead employs method B, which has really only been possible with the cosmic origin spectrograph, which has 10 times the sensitivity of STIS. And so in this particular example, what you do is you go hunting for quasars nearby in projection to galaxies, and you can select a galaxy sample based however you want. In this case, we chose L-star, Milky Way luminosity galaxies. And so you hunt for these quasar galaxy pairs. You know the redshift of the galaxy, and then you take a spectrum of the quasar, not knowing anything about the absorbing properties, and you go hunting for absorption at the redshift of the galaxy. And so this is really a galaxy-motivated study of absorption, galaxy halo survey. And this is cos halos. This was an HST COS large program with the principal investigator being Jason Tomlinson at Space Telescope Science Institute. I've been working at UC Santa Cruz, primarily with the astronomer formerly known as Jason X. Kachaska. And a couple of the relevant things about cos halos is that these are selected to be Milky Way luminosity galaxies. We have red galaxies and blue galaxies, quiescent galaxies, and star-forming galaxies. We actually make the cut between red and blue in a spectroscopic way, so I'm going to try not to call them ellipticals ever in this talk. So we've got 15 quiescent galaxies, 29 star-forming galaxies, along 39 quasar sightlines probed with COS. And so these are high signal-to-noise data, and I'm going to show you some of what we find. And in particular, I'm just going to move into the cool gas. And so what you see here is just a kind of illustration of this experiment. You've got a quasar, you've got a galaxy, that's 15 kiloparsecs in projection from the quasar and the rest frame of the galaxy. This galaxy is fairly low mass for our sample. I think actually in the end we ended up cutting this one from our sample, but you see its number here, it's the first, so I just put that one in there. But anyway, you get the redshift of the galaxy very precisely from spectroscopy. You know it to within 20 kilometers per second or so. You go into the spectrum, hunt where you would expect Lyman alpha to show up, and boom, there's some Lyman alpha. And you can do this for the entire cos halo sample. Here's a quasar, here's a galaxy, now 60 kiloparsecs away. You know the redshift, you go hunting for Lyman alpha, there's some Lyman alpha. There's a galaxy, there's a quasar, redshift, Lyman alpha. Galaxy, quasar, okay. So I could go through the entire sample in this way, and I have, and instead I could show you this plot which kind of sums things up nicely. So on the y-axis here you have the equivalent width of Lyman alpha, which you'll note is quite high. And then you have the impact parameter. This is in the rest frame of the galaxy, how far out into the halo we're probing. Cos halos, as you'll see, only goes out to about 160 kiloparsecs, which for an L-star galaxy at Z of 0.2 is not the virial radius. The virial radius is probably like 250 kiloparsecs. So we're not going out to the full virial radius, we're truncating it into the inner halo. Okay, so, but what you can see here, and red galaxies are these diamonds, blue galaxies are these squares, and what you see is Lyman alpha is ubiquitous around L-star galaxies at Z of 0.2. There's not really a statistical difference. Chris Tom did this test. There's not a huge statistical difference between the red galaxies and the blue galaxies. You would note that the only two galaxies with non-detections are red, but I don't know, that maybe environment matters. Anyway, we don't know much about environment. I'll talk a little bit more about that later. You can convert this into a column density, and of course you have to do so very conservatively. And you end up with a lot of lower limits on the H1 column density. This is because our data are affected by saturation, and we don't always get a full Lyman series. But what you'll note immediately is the presence of cool gas around both red and blue galaxies. So there's no obvious suppression of cool gas around massive quiescent galaxies. That's really the first point. It's not only H1 that you see, you also see low ionization state metals, and like Joe, these low ionization state metals are kinematically very similar to the H1 when we especially go down the full Lyman series. And so in particular, I'm showing here magnesium-2. This is what we get with Keck-High-Res data. And you can see that the equivalent width of magnesium-2 and the column density of H1 are tied together, so this is an effect of H1 column density. But what you'll note is that there's about a 50% covering fraction of the metallic ions. And of course, impact parameter matters. There's a declining trend with increasing impact parameter. We actually think that that's a density effect, but I'll talk a little bit more about that. But again, there's not a statistically significant difference between blue galaxies and red galaxies. There's low ionization state gas and H1 around both blue and red galaxies alike. So you can move up to the intermediate ionization state metals, silicon-3, carbon-3. This is what I've been spending my time on. And they're even more common than the low ionization state lines, like silicon-2 and carbon-2. You've got about a 70% covering fraction out to 150 kiloparsecs. And again, there's not a statistical difference between the red galaxies and the blue galaxies in terms of covering fractions. So what we see is cool gas around red and blue galaxies. The gas is highly ionized, and that means that most of the hydrogen is ionized, therefore unobservable directly. So if we want to find out how much cool gas there is, we have to model it, and we have to do, I've done, as Joe has done, cloudy photoionization modeling. And in fact, the uncertainty in the slope of the extragalactic background ionizing spectrum is probably the largest source of systematic uncertainty in these results. But what you can do with these data, and because we have lower limits in H1, is make a very conservative lower limit estimate as to how much cool gas is in the halos of normal galaxies in the local universe. And you can do so because what we can do, we have all these sight lines. We've constructed a sort of statistical map. We don't have just one galaxy and one line of sight. We have 44 lines of sight that go from 10 to 150 kiloparsecs. And so what you can do with this is make a sort of surface density map. You've got a near 100% covering fraction of hydrogen, and so you can get a total hydrogen when you perform the ionization corrections using the individual ionization states of these low ionization state lines, and you find a lot. And these, again, is a very conservative lower limit to the total amount of cool gas. You find total hydrogen columns. You can fit some kind of curve to this if you wish. But in the end, you can just use it as a surface density out to 150 kiloparsecs. The CGM could very well extend beyond that. We've certainly seen that it goes out to 300 kiloparsecs. Other studies have gone beyond that, but instead I'm just going to truncate at 150 kiloparsecs. I'm going to use the lower limits of H1, and what you do is you get a very conservative estimate of 6 by 10 to the 10 solar masses of cool gas in the halos of normal galaxies, cool 10 to the 4 Kelvin gas. And so this is a lot. This is about as much, if not more, than in the interstellar medium of the galaxies themselves. And so it's been discussed that there might be a missing baryon problem on halo-sized scales that when you just consider the stars and the gas and the disk of a galaxy, you're only accounting for about 10%, 10 to 15% of the baryons that are expected to be in a galaxy halo if galaxies are at the cosmological fraction of 17%. So where are these missing baryons? Are they just not there? Did they never fall in? Well, now we know at least a huge fraction of them are in this cool medium surrounding normal galaxies. And so you can make a nice bar plot. And you can see these are, again, my conservative limits. Even the hashed area, this is the conservative lower limit estimate for the cool gas in the halos of these galaxies. There's also, it turns out, the CGM is a multi-phase medium. There's oxygen-6. There's other lines that don't fit in these cool gas solutions. So actually, let's talk now about the oxygen-6, because I mentioned this dichotomy. So Jason Tumlinson in 2011, this was the first result to come out of COS halos, with which some of you may be familiar. But when you look at the high ionization state line of oxygen-6 as a function of impact parameter, we've got column density of oxygen-6 on the y-axis, now impact parameter on the x-axis again. And you can see that there is a difference. I think your eye can actually pick it out, that there is a difference between the blue galaxies and the red galaxies. And just to drive this home, you've got the blue, and then you've got the red. So oxygen-6 is considerably more common around star-forming galaxies than the massive, ellipticals, I should have cut that out, massive quiescent galaxies. That is, star-forming galaxies have a covering fraction of about 90% in O6, whereas red galaxies have a covering fraction of about 30% in oxygen-6. And it actually looks like this is driven by star formation. Now you can put specific star formation rate on the x-axis, and you see that lower star formation rate galaxies don't have as much oxygen-6. And so these are the three key observational realities that come out of the COS Halos survey. And I think that they provoke some questions. And in particular, equilibrium considerations. What's the origin and fate of this massive cool gaseous reservoir at 10 to 150 kiloparsecs from a galaxy? Will this cool gas drive new star formation? And then what are the physical conditions giving rise to oxygen-6? How do they differ from the low ionization state gas? How does oxygen-6 coexist with the cool gas? And why is oxygen-6 an absent ionization state of oxygen around quenched galaxies? And the last question, does environment matter? I put that up there because, not because I'm going to answer that question, but because I want to plug a survey that I'm doing now. This is a large program in Gemini, and you have to do, it turns out, a lot of spectroscopy in the fields of these quasars, very deep multi-slit spectroscopy. And so that is what is coming, investigating these questions of environment. But in particular, I want to say two things about the first two questions. I'm not going to answer them exactly, but they're two clues as to what's going on physically. So it turns out that when you do this cloudy modeling and you get ionization parameters, you can derive a volume density of the gas. You can get cloud sizes, as Joe was mentioning. Cloud sizes could be small, not very high volume filling factors, but you can see the density here. The mean density is about 10 to the minus 3.5 or so for the cool gas in this halo. And so you can do a simple thing, and that is you can consider cool clouds in pressure equilibrium with a diffuse hot halo gas. This is the famous Moe and Morel-d'Escoué work from 1996. And so Mallory and Bullock took that a step further. They predicted a hot gas density profile that evolves adiabatically from the original NFW distribution. And so in this case, cool pressure-supported clouds condense out of a hot medium. This is a very simple picture of the origin of the cool gas. So do the densities that we derive for these cool gas clouds in the circumgalactic medium fit with this picture? And the answer is no. Here's the cool density curve from the previous that we derived from cloudy, and it sits right on top of where the hot gas density should be. This by several orders of magnitude. And so this isn't just slop in the extragalactic background UV slope. It's about, I talk a lot about systematic uncertainty in my paper if you ever want to go read it. But it's not that. And so physically we rule out a very simple model that includes cool clouds in pressure equilibrium with a hot medium. Also, of note, at these densities, cooling times are still very short. They are shorter than 10 to the 8 years. Okay, so another point I want to make, and this is related to oxygen 6, and this is new work that I'm doing, and it's the absence of nitrogen 5. And so you can see, you can make stack plots. You don't have to make stack plots. Our data are good on a sightline by sightline basis, but let's just look at the CGM in aggregate in stacks. Nitrogen 2, nitrogen 3, silicon 4. I could show you magnesium 2, silicon 2, but the point is I'm showing you nitrogen 2 and nitrogen 3. There's nitrogen there in the low ionization state gas. It fits in very well with our cloudy modeling. It's consistent with the silicon 2, silicon 3. It's consistent with the carbon 2 and the carbon 3. So there's no nitrogen 5. Is this consistent? So nitrogen 5 is probably, it's at least the closest ion that we have to the ionization potential of oxygen 6. And its absence is actually very constraining in terms of what ionizes oxygen 6. So you can make a plot, something like this, and actually HVC people have been making these ratio plots for a long time. And so do note that these are all limits. Nitrogen 5, oxygen 6, silicon 4, oxygen 6, silicon 4, some of it's probably in a cool phase, but actually there's too much silicon 4 that we detect for all of it to be in the cool phase. And you can make these arguments, but what you see is a locus of points here, many of which are going to lie over here or down here. And immediately the simple photoionization models for oxygen 6 and nitrogen 5 are ruled out. Oxygen 6 is not photoionized by an extragalactic UV background. That might not surprise a lot of you, but it's something. I think collisional ionization, which are the curves down here, non-equilibrium and equilibrium. There's also photoionization in non-equilibrium over here. They don't work so well either. And I only say that just because the silicon 4 is not all in the cool phase. You can constrain this from the previous cloudy models of the cool phase. A significant fraction of it has to be in a warmer phase if you're going to invoke a simple two-phase model. Now, three-phase models, who knows? But what you can see is they're too high over here for the collisional ionization. So the one line on here that does seem to fit is something that Sebastiano might talk about, and this was done for a purpose that was not cloudy modeling of the circumgalactic medium. He did this to solve the cooling problem, but he recently told me that it was to solve all problems. So, in any case, you include soft X-rays coming from a galaxy, and in here I had to evoke a really high star formation rate. I had to tune some knobs to an absorbing column from a galaxy, but it looks like you can actually fit these. So you can also invoke more exotic models. High-velocity cloud people have talked about turbulent mixing layers and conductive interfaces. Actually, these two are ruled out completely. Turbulent mixing layers just lie in the complete wrong part of the diagram, but these conductive interfaces of clouds in a hot medium don't produce enough oxygen 6, the sheer column of oxygen 6. We get 10 to the 14 and a half. you can't make more than 10 to the 13 in oxygen-6 with conductive interfaces. But shock ionization and a model in which gas radiatively cools by recombination work. The reason that Sebastiano's model works well is this bump around 10 Rydberg. And I'm going to go through this a little quickly, but I'm not going to go through this because I'm done. But anyway, what's interesting about this, and I'll just say this, it doesn't really offer any physical insight on the quenching problem, but including such a model where escaping soft X-rays from a galaxy in your background, your photoionizing spectrum, getting this 10 bump, it naturally explains the O6 dichotomy, because non-star forming galaxies wouldn't have this bump of soft X-rays coming from the stars forming in them. So I like that. It's a simple thing. Of course, shock ionization also works. Anyway, I'm going to leave you with my 3 undeniable observational realities and a couple of the physical insights up here. Thanks.
Thanks. Questions? Actually, somebody who hasn't asked questions this morning.
In the densities you showed in talks about distance, so you reach like the distance of the sun, right? 0.1 virial, right? And the point is that the gas density near the sun is maybe 0.1 centimeter per centimeter cubed. You derive 10 to the minus 3, so you're 2 orders of magnitude below what we see near the sun. So how do you explain this difference?
1 virial is not near the sun.
The sun?
I said the sun is roughly 10 kiloparsecs away, right? And that's roughly the distance that you showed.
Sorry, I'm talking about from the disk of the galaxy. Distance from the disk of the galaxy. I'm not in the interstellar medium, so you've got a galaxy. We're 10 kiloparsecs from the edge of the disk of that galaxy.
From the disk, so you're above the
Yeah, sorry, I should have clarified that. Yeah.
Yep.
Yeah, I just want to point out some other mechanism, something I brought up with Ben Oppenheimer a while ago. So because these densities are so low, the recombination times are long. So if there's some level of Seyfert activity in these galaxies, that once every few 100 million years there's some Seyfert activity, and the ionization models are completely off, because then the high ions would reflect that radiation field.
Oh, that's terrific fun.
Do you make a bump?
Well, it's not like that. You get then some hard radiation from the QSO, and you boost oxygen 6.
But you
right?
also
So
probably
it's-
boost nitrogen 5.
It all depends on the timing. So we show that you can actually get very complicated things. There's, for example, the science paper from Todd Tripp, where he had cold gas as well as hot gas. We can get all of these things at the same time. You have almost infinite freedom, because now the history matters. So depending on when you look at it.
Wait, what paper is it?
Is Oppenheimer and Shea 2 papers last year?
It was last year.
But
Okay.
it's
That's
actually-
funny. Ben made a bunch of curves. Like I've been talking with Ben about this result, and he didn't even mention that. He made these non-equal.
Well, that's bad for you. It's actually hard to get around. It's actually hard to get around it, because there should be such activity every million years or so.
Can I actually comment on that?
Yeah, a quick comment and then
The
Frank.
Seyfert spectrum doesn't help because it's a power low. You need something with a bounce. You need something with thermal.
In equilibrium, but if you have the history.
But you could have an absorbing spectrum. Or you need something with absorbing and creating this bounce. So you need a Seyfert plus an absorbing bounce.
Frank.
It's a more general question. It is still a low redshift. We're missing about 40% of the baryons. The idea is they're in the warm, hot intergalactic medium, and the way I always thought about it, this is sort of the gas that is gravitationally shock heated by the formation of the pancakes and the filaments. You're probably far enough out, you start to see that. I mean, you didn't talk about it.
No, we're not
Have
probably
people
far
have?
enough.
I keep getting confused whether people have or have not detected this now with oxygen
No,
6. So
but
is that still missing?
oxygen 6 is basically unconstrained, but you can put similar limits on oxygen 6, and when you sum up all the components in what you think are the CGM, you can actually account for 100% of the baryons of
But
galaxies.
this is within the virial radii of dark matter.
Within the virial radii of the dark matter.
It's 300 kbc, is it?
Yeah,
It's-
but that's 250 to 300.
Joel, and then I saw somebody.
Yeah, Jess, some of your absorption line systems lead to extremely long path lengths.
That's
And you mentioned that in the paper, you have path lengths that are a few megaparsecs.
that's the maximum. of
have-
it, yeah, it's
well,
it's
it's what you
really
get.
large. Yeah.
Yeah, and then if you
Like I
figure
said,
that
though, they're
spherical,
limits.
that they're not little things,
Right.
then that leads to a mass of the cloud in excess of 10 to the 13 solar masses.
Those are limits, and that's not actually how I calculate the mass. I don't know if
Well, they're not limits. You get a column.
yeah,
You get a density.
that's right, but the column is
You
sometimes
divide
a
the column by the density, you get a path length. 4/3 pi r cubed.
That's right.
Length times the density, and you get a mass. So you get these,
Right.
in some cases, you get gigantic masses.
That's
we
not
don't-
how I
that we
calculate my
don't
masses,
see.
though. I would just like to say.
But that is what you infer, that's what you get from your fix, right? You get a very long path length.
Not for all of the clouds, but for some of them
No,
they do.
not for
They
all of
do.
them, but
They are large.
the analysis
They're
is
uncomfortably
leading
large.
to some truly gigantic masses that we don't think really do exist. I mean, 10 to the 13 solar mass clouds with nothing in them.
I don't think I ever said that there was a 10 to the 13 solar
But that's
mass
what you,
cloud.
well,
I
you may not
said that
have
there were
written
problems
but
in that particular
if you figure out the
analysis.
mass associated with your absorption system,
Mhm.
in these cases, you do
In
get
the
masses
individual
that big.
absorption system.
And you do get path lengths that are, in many cases, hundreds of kiloparsecs long. And-
If the filaments like what
Well-
they showed, then you can use it as estimate. Just occasionally they happen to look on the filament. Maybe
But-
they're on, occasionally
Well,
they're
you
on.
can worry about filling factor and things like that. It's somewhat of an endemic problem with photoionization models, in that you get very low densities, very low pressures, and consequently, extremely long path lengths. It's not just your work. So I'm saying that, this should make us feel a little uncomfortable.
One last question from Brent, and then we should take a break.
So what constraints do you have on the difference in the alignment between the oxygen 6 and the lower ionization?
Yeah.
Is it how well can you constrain the shock model from alignment?
Yeah, actually, that's a really good question, and we're working on a kinematic analysis right now. So it's funny. Oxygen 6 is sometimes it lines up perfectly with the lower ionization state lines, and sometimes it doesn't. And so it's. I think more times than not, it lines up well with the lower ionization state gas, and then sometimes it's a little broader. That's my assessment at this point. We're doing a quantitative analysis, so stay tuned.
Let's thank Jessica again.